Introducing geometric sequence. So we have a sequence A1, A2, A3, A4, A5, 6, and then we go all the way to AN, and then after AN we keep on going. So this is an infinite sequence. What is the difference between the sequence and the series? So a sequence is a list of numbers separated by commas, and then the series is the sum of this list. So if I'm talking about geometric series, then we are adding all the terms together. So for a geometric sequence, there is a common ratio. The common ratio we use R. R is equals to A2 divided by A1. So when I was studying geometric sequence, when I was a student, I am thinking about this is as the next term divided by the current term. So A2 divided by A1, A3 divided by A2, A4 divided by A3. So if you are stepping on step 3, you are taking step 4 divided by step 3. If you are standing at step 4, then you are taking step 5 divided by step 4. If you are standing at step 5, you are taking step 6 divided by step 5. So basically they come in pairs. You take the next term divided by where you are currently standing. And then the ratio cannot be equal to 0, because if the ratio is equal to 0, the numerator has to be equal to 0, right? So think about this. When A2 is equals to 0, A2 divided by A1 is equals to 0. This is bad, because when you reach to the next term, A3 divided by A2, you cannot have a 0 in the denominator. And that in general, for the nth term of a geometric sequence, that is an equals to the first term times r raised to the n minus 1 power. I color-coded everything for you. So the nth term, the nth power, the first term, and then the first power. So let me give you a few examples to study geometric sequence. So the first one, I have a list of number. I say that this is a geometric sequence. So for n equals to 2, this is the initial term. N equals to 1, n equals to 2, n equals to 3, n equals to 4, n equals to 5, n equals to 6, and then we keep on going. And then what else can we say? This is a geometric sequence, so there is a common ratio. So the common ratio, so let me write this down, common ratio, which is R, that is equals to 4 divided by 2, which is equals to 2, right? And then as always, I always use this. I always check a couple more pairs to make sure the common ratio is right. I will take 8 divided by 4, and then that is equals to 2. 16 divided by 8 is 2. 32 divided by 16 is 2. 64 divided by 32, so they are all equals to 2. That tells me that what happened? This is a geometric sequence. The ratio applies to every single pair. And then how about the nth term? I know we have the nth term right over here, but I want to try the formula anyway. So the nth term, so we have an, which is equals to the first term, a1 equals to r. Did I say? I brought it equal r to the n minus 1. The first term is 2, and then the common ratio is also 2. And then this is r minus 1. So take a look. Oh, r minus 1, huh? R minus 1, n minus 1, n minus 1. And then can we simplify that? Yep. So they are both base 2. The 2 outside of the parenthesis is raised to the first power. So once you add a first power to the n minus 1 power, this is equals to 2 to the n, which is what we have right over here. So this just confirm my answer. Now, using the nth term, what we can do is, what happened when n is large? So what happened when n is equals to 100? Then you have 2 raised to 100 power. So this is very close to, infinity. So that means in this geometric sequence, so as n becomes extremely large, as n approaches, the arrow stands for approaches. So as n becomes very, very large, so what happened to the nth term? The nth term is 2 raised to a very large power, and this is just an infinity. So if you are studying geometric series, when you add all the terms up, the sum is just infinity, very, very large. Because as we move on, these terms are getting so large, when you add them all up, the sum is extremely large. All right, so let's try the next one. The next one doesn't look that obvious compared to the first one. So I claim that this is a geometric series. All right, it's fine. We will just test the common ratio. So common ratio, which is equals to ratio, which is R equals to the second term divided by the first term, 1 over 9 divided by negative 1 over 3. So what is that equal to? This is a 3 over 9, which is negative 1/3, right? So I am not, in order to, to be more confident, I want to try a couple more pairs. So how about negative 1 over 27 divided by 1 over 9? So 9 over 27 is 1/3. So if you try another pair, 1 over 81 divided by negative 1 over 27, you do the math carefully, you will find out that the common ratio is always negative 1/3. So that tells me this is a geometric sequence. And then what else? The nth term. So we have an, which is the first term, times r raised to the n minus 1. The first term is negative 1/3. Common ratio is also negative 1/3. And then n minus 1, so you add 1 to the n minus 1 power. As a result, this is a negative 1/3 raised to the n. And then the problem just confirmed that my answer is right. Now, what happened as n becomes extremely large? So what happened when you find a 100th power? So this, you will have negative 1/3. When you have a number between 0 and 1 or 0 and negative 1, you raise a big power like this. So to make this simple, how about 0.2 and 0.5 raised to a very large value? You can try this in your calculator. So let's say 0.2 raised to 1000 power. When you take 0.2 raised to 1000 power, the product is extremely small. So this one is nearly 0. It's nearly 0. So that means as n approaches to infinity, and then the nth term approaches to just a 0. Why do we need to know this? Because later on when you study geometric series, you are adding every single term up, right? So you are adding every single term up, but when the n gets very large, the terms right over here, all the way on the right hand side, they are just a bunch of 0. So that means the sum is really determined by the first couple terms, because when you raise to a large power, you get a bunch of 0. So when you are adding up a bunch of 0, that doesn't change the sum. So that's why I said that the sum is determined by the first term when the exponent is small. Compared to the previous problem, the 2 to the n, as n becomes really, really big, you have a bunch of infinity. So when you add up a bunch of infinity, the big sum is just an infinity. All right. So moving on to the purple problem. To save myself a little bit of space, I'm going to move this problem up. All right. So this one, I didn't tell you the nth term. What should I do? So if I didn't tell you the nth term, so let's don't say that this is a geometric series right away. So let's try to be brave and then just try something. So the common ratio is the next term divided by the first term. So this is equals to, oh, it's also another negative 1/3. Let's see if that applies to the next pair. 3 divided by negative 9. Yup. And then negative 1 divided by 3, yep, is always negative 1/3. So this is a geometric series. So geometric, did I say series? Geometric sequence. Geometric sequence. And then the common ratio is negative 1/3. And then what else? Where is the first term? The first term is 27, right? So a1 is equals to 27. And then how about the nth term? The nth term is, you have the first term, a1, and then times r to the n minus 1, which is 27. And then the common ratio, and then n minus 1. That's it. Moving on to the red problem. So the red problem, same thing. I'm trying to save myself a little bit of space by moving this up. So that one is even less obvious compared to the purple problem. So that one, just be brave. Go ahead, take a first step. So the common ratio is the second term divided by the first term. What is that equal to? That one, if you do the math right, so this is equals to 2 over square root of 3. 2 over square root of 3. Okay, this one, sometimes you have to rationalize. Rationalize means no square root in the denominator. You have to do that by doing multiply top and bottom by square root of 3. Keep both. right? Keep both. So this is a 2 times root 3 divided by 3. You have to rationalize. Keep both. Okay, we try two more pairs to see if that works. So we have a over 3 divided by the previous term, 4 over root 3. So a over 4 is equals to 2, right? So we have a 2, and then you flip the root 3 up, and then this 3 is in the denominator. Okay, I'm fine with that. And then the next one, you have 16 over 3 root 3, and then you divide it by a over 3. So 16 divided by a gives you 2. In the denominator, you flip the 3 up, just the top multiply the reciprocal of the denominator. And then the 3 root 3 goes to the bottom. As always, you have to rationalize by multiplying the top and bottom by root 3. So that one, the 3 is gone, right? So you have a 2 root 3 divided by 3. So check, check, check. And then we say that this is a geometric series. Geometric series. Did I say series? I keep saying series. Sequence. And then the first term is equals to 2. And then the r is equals to 2 root 3 divided by 3. And then these are the ingredients to draw the nth term. So the an, which is equals to the first term, times the common ratio, 2 root 3 over 3, and then raised to n minus 1 power. There is no need to simplify this any further. Okay, we have two problems left, and then I will move on to another video to use more example to show you geometric sequence. So we have the first term, we have the common ratio. I want to find the next four terms, and then what happens as n becomes very, very large. Okay, let's recall. We call the nth term. So the nth term is equals to a1, and then rn minus 1, right? So we got the first term, we got the r, we can write the nth. So this is 2, and then the common ratio. I would not rationalize this right now, because we can do that as we plug in more numbers. All right. You know what? This one, I would just try to make this problem simple. You know what? I would just do a 1 half. You can stick with the root 2. I will just try to do a 1 half, because on my notes, I use a 1 half. I already have everything prepared. I don't want to change stuff when I am because when I am talking, filming, recording, and then changing number, that is so easy to make a mistake. I prefer to stick with my notes by changing the r back to a negative 1 half. Okay, you can try negative 1 over square root of 2. That's fine. That doesn't change the result too much. You just have to deal with like the rationalizing. Okay, what happened when n is equals to 1? When n is equals to 1, so you have 2, negative 1 half, 1 minus 1, then anything raised to the 0. Any non-zero raised to the 0 is 1, then this is just a 2, which is the given. And then the second term, you have negative 1 half, 2 minus 1. So 2 times negative 1 half is negative 1. And then you have the third term. So the third term is, let's move up, 2 and then negative 1 half, 3 minus 1. So you have a 2 times 1 over 4, right? Square, you get rid of the negative. That is a 1 half. And then the fourth term, you have 2, negative 1 half. Basically, you are changing the exponents only. Yeah, so switching the common ratio to 1 negative 1 over square root of 2 shouldn't change much. And then this is a third power, so 2 times negative 1 over 8, then this is a negative 1 over 4. And then the fifth term, you have 5 minus 1. 5 minus 1, then the fourth power is 16. 16, so 2 divided by 16 is 1 over 8. What happens as n gets extremely large? So as n gets extremely large, you have 2, negative 1 half, and then 100 minus 1, all right? 99 power. So this 199 power, what happened? 99 power, so here, this one. you have a very large exponent, so this is very close to 0. As a result, the 100th term is very close to 0. Try negative 0.5 or 0 0.5, 0 0.1, 0.3, 0.4, 0 0.25. Anything between 0 and 1 or any decimals between 0 and -1, raised to a very large power, you will get something that is so close to 0. So that means as we move on, as n becomes extremely large, those terms are just a bunch of zeros. All right, so I can say that as n approaches to infinity, as n becomes very, very large, those nth terms, n minus 1, n plus 1, whatever the heck that is just 0. Okay, last one. You got A1, you got the R. Okay, find the next couple terms. So we have AN equals to A1 and then R raised to the n minus 1, which is 5, and then e to the negative x, n minus 1. Nothing else can be simplified. I got the AN, the 7th. This is a 5 e to the negative x, 5 minus 1. So you have 5 e to the negative x to the 4th power, 5 and then e to the negative x times 4, and then a to the 20th. So you have 5 e to the negative x and then 20th minus 1. Then you have a 5, 19. So 5 e to the negative 19 over x. And then I think that's it. So you can put that as, I would just not going any further. Yeah, it is what it is. Okay, now this is the end of this video. If you like the way I introduce geometric sequence, give this video a like. If this is something that you would like to watch, subscribe to my channel for more content. As always, I will meet you all in the next one. Signing out.